we can see about energy band diagram and breakdown in PN junction diode. In the case of energy band diagram, the region of the left on the left is p type, which with an acceptor density Na, and also the region of the right is n type, which is the donor density. And here the dopants are assumed to be shallow, so that the electron density in the n type region is approximately equal to the donor. Here this is the diagram for the equilibrium. While we are seeing this, to reach the thermal equilibrium, the electrons holes close to the metallurgical junction diffuse across the junction into the n type and p type region, where hardly have any electrons and holes are present. This process leaves the ionized donor behind and creating a region around the junction which is depleted for mobile carriers. And this region of the depletion region extended from x equal to minus sp to x equal to np, and the charge due to the ionized donor and the acceptors causes an electric field, which in turn causes a drift of carriers in opposite direction, and the diffusion of carriers continues with the until the drift current balances the diffusion current, thereby reaching the thermal equilibrium as indicated by the constant Fermi level. And this is in equilibrium, thermal equilibrium. No external voltage is applied across the n type and p type material. There is an internal potential which is caused by the work function difference between the n type and the p type. And here this is said to be the energy band diagram of the PN junction under the reverse and forward bias condition. Here, in this PN junction with an applied bias voltage VA, a forward bias correspond to the applied positive voltage to the diode related to the cathode, and here the reverse bias corresponding to the related negative voltage applied to the diode. The basic voltage applied voltage is proportional to the difference between the Fermi level in the n type and the p type and your quasi neutral regions. As the negative voltage is applied, the potential across the semiconductor increases, and so then does the depletion layer width. As the positive voltage is applied, the potential across the semiconductor decreases, and within the depletion layer width and the total potential across the semiconductor equals the built-in potential minus the applied voltage. Here next, this is already we have seen. This next one is the breakdown in PN junction diode. Here in this, when a PN junction is reverse bias, it allows very simple small current to flow through it, and this current is due to the movement of majority charge carriers, and it is almost independent of the voltage applied. And if the reverse bias is made too high, the current through PN junction across the abruptly, and the voltages at which this phenomenon is said to be the breakdown voltage. And here at this breakdown voltage, the crystal structure breaks down, and this crystal structure returns to the normal state when exceeds reverse bias is removed, providing that overheating has been permanently damaging the crystal. And there are two processes which causes junction breakdown. One is Zener breakdown and another one is avalanche breakdown. First we can see about Zener avalanche breakdown. Here avalanche breakdown is increased electric field causes the increase in the velocity of the minority carriers, and here this high energy carriers break covalent bond, thereby generating the more carriers, and again they are generated carriers are accelerated by the electric field. They break more covalent bonds during their travel, and chain is then established, creating a large number of carriers. This gives rise to a high reverse current, and this mechanism is said to be the avalanche breakdown. And next one is Zener breakdown. Here in the Zener breakdown, when increases the reverse voltage across the PN junction diode, which really happens is that the electric field across the diode junction increases both internally and externally. This results in a force of attraction on the negatively charged electrons at junction, and this forces electrons frees electrons from this covalent bond and moves those free electrons to conduction band. When the electric field increases, more and more electrons are freed from this covalent bond, and this results in drifting of electrons across the junction, and electron holes recombination occurs. So a net current is developed, and it increases rapidly, which increases in electric field. And the Zener breakdown phenomena occurs in a PN junction diode with heavily doped and thin region junction. Here the Zener breakdown does not result in damage of diode, and thus the current is only due to the drifting of electrons. There is a limit to the increase in the current as well as current as well. This is about the Zener breakdown and avalanche breakdown. Thank you.